This video will show you the principles how to work with FrameJoin Pro. FrameJoin Pro gives you the option to analyze a variety of bolted, rigid or semi-rigid connections for I-beams or columns made from I-shapes. It can be a knee connection, it can be a connection with a continuous column, it can be a T-type of connection, it can be a cross connection, can include backing plates and web stiffeners. It can have a tapered connection and it can be different on both sides if you like to. There is a great variety of connections you can use FrameJoin Pro for, and it is used for typical I-beam or I-column connections. The module has a layout mode where the software provides you the number of bolts. It will give you a suggestion about the spacing of the bolts, also about the required stiffness and the thickness of the plates, and also it will lay out the welds for you. If you go to the checking mode, you will have to enter all these dimensions by yourself and the number of bolts by yourself and also the size of the welds. So the recommended way how to do it is first to perform a layout and then select from a suggestion of the connection, from a suggested layout of the connection to the real connection, and then do the verifying of this connection. If you have to check an existing connection and you're not free in the layout, you can right away select the check mode and you can enter your dimensions all by yourself. However, this is more work and you have to think more because all values might depend from each other and it's not as simple as you might think. We use the Eurocode design modus for the analysis of the connection, and it's called the component method. You are very flexible in the geometry of the connection, and also it's only just one program. It covers a wide range of connection types. You can do also a so-called classification of the connection using the elastic analysis, as is it called in Eurocode, and it's a classification by stiffness. That means you can analyze the stiffness of such a connection and get the spring constant for such a connection that you can insert into RFEM or RSTAB if you like to. Maybe this is all for the short introduction, and next I would like to go to the model and show you the module live inside an example. We have here a typical steel building. There is two different frames in this building. One is this 2-bay or this 2-hinge frame, and one is another frame that has a center column. We want to do two different connections. One is here for this 2-hinged moment frame. There are 6 locations where we have the same connection, and we will design all this, we'll check all these situations and design a connection for this. To do this, first of all, you have to create all your load combinations as it has been done before. And we have here a set of load combinations, and at the end we have a set of result combinations for the ultimate limit design. So this we will use for the design of the connection. First, we find the module in the list of the add-on modules, FrameJoin Pro, designed of bolted frame joints. Using a double click, we can start the module. In the first window of FrameJoin Pro, we'll have to first select the nodes where we want to design the connection for. We just pick the nodes by clicking them one by one, and the node numbers will be shown in the little selection window, and we click OK. By doing so, FrameJoin will automatically find the right joint type. So in this case, we have a knee joint. It's important that we have all the nodes, have the same set of columns and beams. The geometry has to be exactly the same. If a beam is longer or shorter, or if it is a different slope in the beam, it will not work. It has to be the exact representation for all nodes. Then next, we will have to choose the code. We have DIN code or Eurocode, and we have national annexes. If you miss a national annex, you can easily create a new national annex, and maybe we do so. We select a country. We can say we want to have the national annex for British Standard, United Kingdom. We can create it, and then next we will be able to set up the safety factors, and I said here, for example, 1.0. This may depend on your national annex. So once you have this, you can select it here from the list. Important to know is also we can choose to import the data from RSTAB or RFEM, or we can do a manual definition. This we'll do later. We'll do a manual definition for another connection where we don't have a model. As I said before, there is several modes. There's the preliminary design of sites, which is a layout mode. And then there's the check with specification of all dimensions. I suggest really to start with the preliminary design of the sites, so you get a rough layout, a rough idea of the connection. After that, it will automatically switch to the check mode, and you can set up more specific values for welds or other dimensions. This third option, which is here in the center, final design with interaction of both sides, is used for a connection where we have two sides. And in the first preliminary design of sides, we will get a layout of both sides of the connection, and then we have to do the final design, which will also do some checks that are referring to the column, where it is important to know which configuration of the connection is at the left side and the right side, and then we can do the final checks where both sides interact in the column. So additionally, checks are done in this final design for the column, and for this we need to know first how the left and right side looks like. So you can note, if you have only a preliminary design, you will not be able to do the full design. You have to do either a check or a final design. In the final design mode, if you're in the design mode, you have still the options to do some layout. If you go to the check mode, everything has to be set in the software. The program will not choose any dimension for you. The design type, you can set whether to calculate all load cases or whether you can do a first preliminary analysis of the governing load cases. I recommend to do a calculation of all load cases. The second options you might need if you have a really big number of load cases, because Instead of checking all individual load cases, it will first analyze the internal forces and try to find the controlling cases, and then do only a design for the governing load cases. If you have a two-sided connection, you can choose to select for a symmetric connection. If you want to, you can have an optional comment here. Okay, we just wander through the input tables. When we have a takeover from RFEM or RSTAB, we will not be able to select any materials or cross sections for the column and for the beams. And the beam at the right side will always be this end of the beam. This is considered the connection, and the beam is the main beam of the frame, and the beam of the frame is an IPE 450 in this case. You see here also the member and column numbers of the beams that we have selected, and you can here check whether it has recognized the beams correctly. In some 3D cases, it might be so that it's not really clear which kind of members or beams belong to that node. You have the choice to select them afterwards, but in general, I think you will not use it. You might find some comments here. If something is wrong, you will get some hint here, and the numbers here will be red. Okay, this is easy. We go to the next part, column part 1. You see here a little window. You can use the wheel to zoom or move the connection. You can also stretch the dialogues to get a bigger representation of the graphic. This is also nice to have. You have here some buttons. You can turn on and off the dimensions. If you have dimensions on, you can set whether there are numbers or whether they are just symbols to be used. Also, you have here YZ isometric view. Also note, if we click somewhere, this dimension will highlight. So if you don't know where you are, you will get a visual hint where this input box refers to. Okay, we are at the columns. We are still here in preliminary design of side modes. So if you go to the column, now we find here those logs. If you want to set in the layout mode already the thickness of this end plate of the column, and you want to set it to 25, you may do so. So there will be a 25mm end plate. If you leave this log open, the software will tell you what thickness it needs. So you have the option to either set something or to let the software to choose something. Sloped end plate means if you have a slope here, you can say sloped end plate, or you can have it straight. You can see what happens. Usually you will have a sloped end plate. If you want to, you can say I need to have a web stiffener at the bottom, or I can prohibit it, so no web stiffener will be there. If I put it to design, the software may put one there if it needs one. And if it needs one, I can say it should be thickness of 20mm. But it's questionable. Maybe it doesn't need anything, then this setting will have no effect. I can forbid it, so there's no check mark in those two checkboxes. You can also have a diagonal stiffener. A diagonal stiffener will be doing a diagonal stiffener here. At the moment I cannot set it for a certain reason. Yeah, there has to be a web stiffener, and then I can have a diagonal stiffener. Same thing again. I can tell the software it has to be present, or I can say design, and then it may be or may not be there. And if it's there, I can set it to a certain thickness. So this stiffener I don't want. Usually it's too expensive, and I don't want it to be there. Again, I turn off the web stiffener off the bottom. Also, it's possible to have supplementary web plate. The little holes you see here are for yeah, welded. The code says if you have a doubler plate on the web, it has to be sure that it's continuously connected to the web. Therefore, we have little holes in there that allows you to put to weld it there, to weld it to the web. So there are some provisions how many holes you have to have, and the software does that for you. If you go to the design mode, it may or may not be there. Typically, it is in the design mode. You can say I want to have it on two sides, or I want to have it on one side. Typically, it will lay that out for you if you want it. And you can say I want to have it at least 20 millimeters or whatever. In generally, when you start, you leave everything as it is. You don't do anything. It's all set up, so you don't have to wonder what to click or not to click. If we go to the next column, input window, we can set up backing plates. So I can say the left side, now we have just a one-sided connection, so the left side is disabled, but the right side it is present. And I can say on the top, I can say on the bottom, I can say continuous, so it will do one plate. And I can have an extended end plate, so it will be on the top, and then you can have also a backing plate in the extension. At this moment, I don't need one. And there's again the design button as you already seen it at other components. Web stiffener, left and right side. If I say present, there is only a partial web stiffener. It's not continuous. And you can use that also in a partial way. Same thing again, design or layout as you've seen it at the other components. I will just leave it maybe at design. If it needs it, it will put one there. Okay, next thing will be the beam. We can set with or without taper. Since we have a tapered cross-section in the RSTAB model, it sets it automatically to tapered here. The depth or the height of the end plate will be set according to the geometry, what we have there. So we can straighten it out because it's kind of hard to manufacture 600.6, but it's the theoretical value that is calculated from the slope and from the cut of the beam. Let's say it will be 600, and the length is the length from the column end to the node of the beam, and because that length is 1550, it shows the value here. You can change it. So for example, you can say I do my preliminary design of the beam without any taper, and the connection design will decide then whether I need a taper or not. So you can do the moment analysis, a moment frame analysis without taper, and then decide here in the connection you might need a taper, you can put one there. If you want to, you can set the depth from the model. You can read it from the model, or you can update the cross section according to the set vertical depth. So it will update the cross section in the model. Think carefully what you do here. I think the typical way how to work with it is you do this analysis first for the beams and the columns. And you take into account that you need something also for the connections, and then you verify your connections. And if you want to really change the depth, you can use those buttons. But also note, we're doing here a more exact geometry in this program than we would usually do in the frame analysis. So what we do is we take usually the center line of the connection and put it into the angle alpha O, and the center line from the eccentricity got here a little slope of 2.53, so I can set it to 0 if I want to have it really horizontal on the top. So you might just check this. You get here also little eccentricity from the node E, which is the system node here in the corner, to the edge here of to the node A, which is at the edge of the flange here. And we have this is a 300 millimeter deep column, so we go 150 millimeter to the right, and then we move down 13.9 millimeters. So this is this eccentricity, which is recalculated from those angles. This is the top angle, this is the center angle, the center line, and this is the bottom angle. Okay. Next will be supplementary web plate. We can have one here, which can be on top, for example. So the load has to go through here, and there might be a supplementary web plate necessary. It can be on the bottom as well, and it can be continuous if you want to. Typically, we want to avoid it, so I really won't use it unless I really need it. The end plate can be top flush arrangement, or it can be with an extended bolt on top, which will be more stiff naturally. Again, you can set the thickness of the end plate. If you click here, you'll see there will be the dimensions, or you can zoom in and then you will see the dimensions of the end plate. And the thickness is T. If you don't like it, you can make it to numbers, or you can turn it off. Okay. For this preliminary design, I think I want to have just a flush arrangement, which will be cheaper. And the thickness, the software should tell me. Also, I can have a beam stiffener. That can be here. There can be either stiffener, which will make these top bolts a little bit more, we'll put more force there. I can also put it up and down. I can say, okay, 200. And after leaving the input field, it will move the stiffener up. Same way I can set the welds and the thickness of the plate. Or what might be more typical is to use a cut section of the beam. So you basically cut a smaller piece from the beam and weld it below the other full beam, and it is simple to manufacture. You just take another part of the beam, cut it in two, and weld it underneath the existing one. So this is also possible, but you have then a 3-flange cross section, which will result into different forces in the bolts and in the entire connection actually. So we leave it as is. In the next part of the connection, I have to select the bolts, and um, the software uses some initial spacing. Maybe I start with a M20 at the beginning. So the minimum spacing is automatically changed if you click to the corresponding value, it will highlight it. Yeah. Automatically, the first bolt row will be as far up as possible. EO means the spacing in between the top um, bolt rows. So if I click here, it will be highlighted. Yeah. You can set the number of bolt rows if you want to, for top and bottom, or you can leave the program to select it for you. And also you can set the horizontal spacing, E3 and E2 here inside if you unlock these locks here. As before, usually I would just go with the initial setting. Uniform arrangement means if you have top and bottom bolt groups, it will just evenly space them out. But typically you will use bolt groups for top and bottom. Okay, if you want to, you can say the compression forces should be transferred by contact. So the grade of the bolts is here. If you check local buckling effects, it will use different spacings, minimum spacings of the bolts. You don't really need this. Tighten bolt or the head and nut means you can gain a little bit more in spacing. Sometimes it's not so simple to arrange all the bolts so they can be mounted correctly. The software checks also geometrical conditions, whether you can put in the bolt, whether there's room for the wrenches and so on. And if you're allowed to tighten it from both sides, it allows you to move the bolts a little bit closer to the edges, because you still can tighten it with the other um, side if you reverse the bolt. If you apply full pre-stress, it will result in a more stiff connection typically. The hole clearance is set usually to 20 millimeters. Okay, the loads, this is quite simple. We just need to select the individual load groups or the load combination or result combination. If you select the result combinations, that includes all the load combinations, you will get as a result, of course, only the controlling this result combinations. If you are interested in wanting to know which combination is really the controlling one, I recommend to select all combinations, and then as a result you will get which of those one will be the controlling one. But the final result of the connection will be the same. You just get this additional information where this controlling load comes from. Okay, take a look at the details. We can perform a classification of the stiffness, which we'll do later. This is only an optical thing. I think you don't even have to explain it. The range dimensions, this is where you can actually set the dimensions of the ranges, and these are set from typical ranges that we use and minimum distances, so it allows you to reserve space to put the wrench on. You can also eliminate compression forces in beams. Um, this is good because if there are compression forces, it will reduce the bending moment in the connection, because um, when there is a connection, the top usually from a negative moment will be in tension, and if there's an additional compression force, it will reduce this tension force in the bolts. So you could eliminate those if you want to. Basically, then you design the connection for tension and for bending moment only if there is a compression force. Typically, we can go again with the standard values. Okay, we run the analysis and we get a suggestion of in total 6 connections. And you can see here, first connection, if you click here, it would be maybe with just one bolt row, which will be good, but it is not what we want. And then okay, now the software is saving in the background, so it takes a little bit, but it will be right back. So we have one bolt row, we have 2 bolt rows, 3 bolt rows, and we have 4. We always select the one which is working at first, but it's quite difficult to manufacture, so we can go back. We get also some design hints. Maybe I show those first. There will be a message if you want to take over the calculated results in the input table. So it will set it to 4 bolt rows and so on, and to have a stiffener. I don't want this, so I say no. There is no failed checks, everything seems to be fine. But there's too many rows, too many bolts, so I'm choosing a 24 bolt now. It will recalculate now those minimum spacings, and I do the preliminary design again. And now I have a much nicer connection with just 2 bolt rows on top. This looks great. I can choose 3 maybe if I want to, but let's go with the 2 bolts. And this one I use for the final design. It will do now all checks after I select this connection, and I get my final result with an overview about the column and beam design, and you see here all the geometry in detail with all the geometrical values. There's a supplementary web plate which you only see if you zoom around. So this we can't avoid, it needs it. We can also look to the design of the column. There's a buckling check that is needed. Buckling of the, actually this is the buckling of the web, the additional plate of the web. We have the welds for the end plate. We have the right side where we have the column flange. We see also the loads where they come from. They come from combination 5. We see here the forces that are recalculated to the cut edge of the column. And we see all the initial and intermediate values for this analysis. For each bolt row we get the yield line length and the plastic moment of the connection, second row the group value, and finally we get the capacity, the moment and the moment resistance, and we get the final utilization ratio calculated from this. So every check, there are about 40 checks depending on the connections, are here, and we will check all the components. Web column, we have the beam flange, so it's the end plate, the beam flange compressive, this is on the compressive force. Then we have the beam web, beam end plate, there's again bending check, yield lines, and so on. The bolt shear, always the bolts which are in the compression zone are taking the shear, the other bolts taking the tension. If there is a negative moment, those bolts are in tension. If there's a positive moment, those bolts are in tension. So we lay out the connection for the negative moment and we check it for the positive moment. So when you talk about the connection design, I think one of the highlight is also that we check for both moments, positive and negative moment. We do also check of or we do the layout mode, which is helpful, very helpful for entering the dimensions. And we have a graphical representation of the connection that we can view here and finally also print into the printout report. Once you have these moments where the software seems to think, it's because of saving. Maybe you want to select saving time of the backup files a little bit longer time distances. Here we see now the end plate, which is the most important picture. So we have the distances here. Maybe we want to have an end plate of 200 millimeters, so I can change the distance. Maybe I don't like this 0.9 and want to make it a little bit straighter, so I can go back. I go to the general data. You see it automatically went to the checking mode, and now if I go through all tables, I have more fields open to enter things. I can take into account all flange welds and so on. We have the supplementary wear plate, which is 12 millimeters on the other side now, which I can see here. I have the column part. There is nothing. Then I have the right beam, and here I have the depth, and it's 597. Maybe I want to do it 600 millimeters, so we have a straight even value. Okay, we have an end plate of 25 millimeters. Vertical retraction at top is 11 millimeters. This is another important thing. The retraction here is 8 millimeters. The end plate is always pulled back from the top flange, so we fit here a fillet weld, and the software automatically does this retraction, and there has to be a minimum of 2 millimeters. So if you want to, you can even retract it a little bit more, but it will leave their space for the fillet weld, and it will also check if the fillet weld has room there. And the same is on the bottom. There is a vertical extension which is here. If you click here, this will be highlighted. So this has to be there. You cannot really change it so easily. Okay. Then we were looking at these distances where we said we wanted to have 200 millimeters, so I change it to 136. And I also want to do this a little bit straighter. Maybe I want here to have 60 millimeters from top, and then this should be 80 millimeters, and there will be 100 from the bottom. So now we have 622 millimeters, which is much nicer. Okay, then we run the analysis again, and now we have a little bit of a problem. The software tells you column flange moment, column flange tension, end plate moment, so it's not quite okay. We can look at the utilization ratio. So we have 7%, 5%, and this is due to the little changes we made. Maybe what I need to do now is really to maybe make the whole, it's M22. I want to have M24 actually. So let's see what happens now. I changed the bolt diameter, but we are not in the layout mode anymore. So there will be geometrically problems, I think, and the software will tell me, it works. So maybe it's just okay. 24 millimeters looks good. Everything is fine, and we can finalize this design. Yes, what we need to do now is to print the connection to the printout report. I select, for example, the end plate for design. Okay, first we need to go here, end plate, and I want to see this picture in my printout report. So I use print, show printout report on OK. I don't want to see this. I want to have it window filling, use it on the whole page to print out report. Yes, okay, I can put here header, end plate, main frame. Okay, I can also print the column supplementary web, maybe on 50% of a page. Yeah, where you can do a connection of the whole, a picture of the whole connection, something like this. Print. Okay. At the end, I also want to see where the connection is. So I select the frame joint case, and you can see here the picture. Maybe you want to do something like this. And we can print this picture, so you have a visual impression where this picture, where this frame joint is on one page. And after that, I want to see my printout report. Selection of the printout report is just like in any other module. There's a tree for Frame Joint Pro, and it has here all your pictures. I had here some pictures from an earlier demonstration, so I don't want to see those. If you want to delete those, right mouse click, remove from printout report, so it will be updated automatically. You can see here another picture, end plate, isometric view. Let's see what happens here. This is this one, end plate mainframe. This one. We had this isometric view, this, and then we had this picture, and this one is too much, so I select it and delete it. And also I can rename this picture, and I say properties web doubling plate. Okay, and this way you can print all your components of the connection into the printout report. You see here also then in the tables all your details of the connection, all the geometry, everything is there. You have also the option to filter the results. FrameJoin Pro results, you go into details, what you want to have there. So you can uncheck it or leave it there. So I suggest to leave it there. It's not really so much that is spent on paper by FrameJoin Pro. Okay. You can see here, first page is on page 8, and then the whole connection will be, we have 19 pages, so there's 9 pages for this connection, for the documentation of this connection. Okay, I think this will be enough for the first part of the design of this connection. Next, we will go and check the stiffness of this connection. And I go back into the FrameJoin module. I open the module and then I will enable the classification. When we do a classification, it will be an elastic classification and a new table will show up here. We can calculate the initial rigidity of the frame joint, or we can define it manually. Usually you will calculate it. Then you will need to tell the program from the 1,000 members that you have which one is the beam, and I can select here just the whole beam. Okay, this one I still need. Go on. This one need. And come on. Okay. Results are on this one and this one. Okay. Then I have the length of the beam and I have the average moment of inertia. Then this is what you need to calculate the limiting values of the stiffness to be classified, to classify the connection to be rigid, semi-rigid, or pinned. And if you have an unbraced frame, you have to check for each story a certain relationship of the stiffness between the columns and the beams. So therefore I need to tell the program which members are the columns and which members are the beams. It's important to identify the length and the average moment of inertia and the length and the moment of inertia of the columns. Note that I don't know any other software who allows you to check this relationship inside the program from picking the members from the model. Usually it's assumed that it is within a certain ratio, so you're allowed to do even the stiffness analysis and in a frame. So after this, I can run the analysis again and I get information about the rigidity of the software. And in the result, it says it's semi-rigid. And if I go to the corresponding side, you will see it's semi-rigid, and I get here the mean ratio of KB and KC, which is calculated from the columns and the beam, which has to be greater than 0.1 to allow this method to be used. We have here the loading moment and the resistance moment. We have here the limit for the rigid and the pinned stiffness. We have here the initial stiffness, and we have the applicable rotational stiffness, which is in the simplest way half of the initial stiffness. When we have a moment above 2/3 of the resisting or the ultimate moment of the connection, you only are allowed to apply half of the stiffness of the initial stiffness. So this is what we need. This would be the spring constant we need to apply into RSTAB. And we get here each component for the stiffness. So what we can do now, we can either apply the stiffness, so we take this value and put it into a spring constant on the frame, or we try to get this connection to be stiff, so we can use, or rigid, so we can use this simplified model. So what I'm doing now is I'm going back to the column, maybe to the part 1, and I'm going to do here a web stiffener. It suggests 20 millimeters, and I run the analysis again. And we will see what will happen. And we have here now a rigid connection. And we can see that the stiffness has changed to a greater value. Come on, here we go. Stiffness rigid. We have here the limiting rigid stiffness is 118,090, and the initial stiffness is greater than this, so we can classify it as rigid, and we don't have to do anything anymore, and we can just analyze it as it is now. Okay, this is what I wanted to show you for Frame Joint Pro, and this concludes my lesson.